Thank you. Thank you for the kind introduction. I will be talking tonight, as is obvious, about rocket science and if it's hard, how hard can it be? And my assistant here, Mr. Sayandeep Shaun Khan, he will later speak about some meteorological experiments. I myself, I'm a physicist, an astrophysicist, and the work we do in rocket science in the FIR is purely amateur rocketry, as you would call it. We are not pursuing any financial gains. We are just doing it because we want to do it. We want to know what is going on with this. Okay, so what is rocket science? It may be something that is really complicated to understand and to learn. That's what they all say. Oh no, it's not rocket science. It's just a synonym for saying that's really easy. So in reality, it's to design, build, and fly rockets, of course. And that's what we do. And if you do it more sophisticatedly, with a lot of money, we call it aerospace engineering. So why would you do that? I mean, it's a lot of time and money and resources, you think. Yeah, why do it? Yeah, maybe you're just curious. Can we do it? Is it possible? That was what had driven the first pioneers, because it was totally unknown if you could reach space using a rocket at first. Then, of course, there's this main driver behind this rocket science, which is technology, where you want to achieve something like project something on somebody else. You know what I mean. And for me as a scientist, as a physicist, it's very interesting to see all these space-borne instruments giving us data that were not achievable from the ground, especially in the infrared. And for philosophers, it's just a treasure trove thinking about the vastness of space and what it means for us as human beings. So, of course, if you can get to space, why not travel? Why not go to other places in our solar system, like other planets, asteroids, or comets? You all have heard about the lander Philae that has landed last month on Churyumov-Gerasimenko's 67P. And I can say this name very well because I've been working on this project. And right now, I'm very proud to say that this lander that has touched down on the comet has my name on it. So, thank you. So, space travel leads immediately to exploration. So there are other spaces, locations around the solar system or even beyond that we would like to go to and explore, that is, look at it, measure in situ, or bring back stuff to measure it here. And of course, if you do this for a long time, maybe in the future we can do colonization. So we can go there to stay and to survive on the long run. So these can be your motivations. Maybe you have another. Tell me. Yeah? If you find something else, I would be interested. So, motivation. Now let's come to the three modern rocket scientists. There were, in ancient times, Chinese rocket scientists. They're not well known, but they were there. But they were not very successful. It's a long story, but today we'll talk about the three rocketeers, as I call them, which is the first one is Konstantin Eduardovich Tsiolkovsky, who lived from the 1860s to 1935. And he was a poor guy because in the age of 10, when he was playing outside in Russian winter, he got scarlet fever and it left him almost deaf. So all his life he was, deaf, almost. So he became a bibliophilic autodidact because he had to drop out of school with 14 because the teacher couldn't get through to him. I mean, yelling all the time at a pupil is very difficult for the teacher also. So he started to read a lot by himself. And he went to Moscow in a library where he met a philosopher called Fyodorov. And he taught him a lot of things. And he read Jules Verne, especially these two little stories called From the Earth to the Moon, and the other one Around the Moon, which is a story about three men being shot by a cannon to the moon and going around. It's the first science fiction story that talks about lunar voyages, and it inspired him. Very fast he understood that it was not possible this way. Anyway, so he became a mathematics and physics teacher, even deaf. And he was tolerated by his environment, meaning that he ran around, mumbled something, and said, it's the old crook, no problem, let him talk. Yeah, nobody understood what he was talking about. He did aerodynamic experiments in wind tunnels, so he built them by himself, and he developed something that we would call today a Zeppelin, full metal, but the Russians didn't understand it, they didn't get it, the authorities wouldn't help him. And he became a philosopher in a branch that is today called cosmism. Very interesting branch. If you want, read it up. So the second one is Robert Hutchington Goddard. And he lived a little later than Tsiolkovsky. Unfortunately, he died very young due to cancer. And he had also a very fragile health, which led to voracious reading. And he was inspired by H.G. Wells. I'm pretty sure he also read Jules Verne, but we know from his diary that he was especially impressed by H.G. Wells. He became a physics professor, which gave him some autonomy and funding. But during his lifetime, he was ridiculed by newspapers, especially by the New York Times. And when Apollo 11 landed on the moon the same day, they, for the first time, apologized in the New York Times for being so bad to Mr. Goddard. He invented and flew the first liquid-propelled rocket, the first that this Earth has ever seen. And, believe it or not, since 1930 he had a workshop in Roswell, New Mexico. Yeah, I can't change it, it's the way it is. And he was sponsored by Mr. Guggenheim. And in the end of his life, he accumulated more than 200 patents that were important for rocketry. That's a number. Anyway, the third one, closer to home, Mr. Hermann Julius Obert. He was also inspired by Jules Verne, and his father, he was a medic, a chirurg. He wanted him to study medicine, so he went to study medicine, but then World War I broke out, and he got wounded in 1915 in the Carpets. And when he saw all this blood and everything, he saw, no, I can't continue medicine, it's not possible. So he switched to physics, math, and astronomy, which has much less blood. And he became a physics, math, and chemistry teacher at a gymnasium, but he was very restless and started to think about rockets. And his ideas that he put forward in the early 1920s were violently opposed by so-called scientists that said what he was thinking about was totally utopian and not possible, and he was a total loon. Anyway, he developed the first German liquid rocket engine. Just a few years later, in 1930, it was the first test, together with his pupil Werner von Braun, that some of you may know. And, interestingly enough, he was a philosopher and parapsychologist. Oh, yes. So, now a few important points in the lives of these three rocketeers that we know of. And one that we know of very precisely because he kept a very nice diary is Goddard's Epiphany, sitting on a charity on the 19th of October of 1899. He has just read H.G. Wells' War of the Worlds and had some chores to do outside, and instead of doing the chores, he went on a charity where he thought about, and he said that it was one of the quiet, colorful afternoons of sheer beauty which we have in October in New England, and as I looked towards the fields at the east, I imagined how wonderful it would be to make some device which had even the possibility of ascending to Mars, and how it would look on a small scale if sent up from the meadow at my feet. I was a different boy when I descended the tree from when I ascended, for existence at least seemed very purposive. So here we have a clear case where a single moment in life changes everything for this man. Then, another very important point, this time for Mr. Tsiolkovsky, was the first publication called The Exploration of Cosmic Space by Means of Reactive Devices, also known as rockets. This image you see here is an early sketch. It's not from the book. He had a refined version there, but it's very difficult to get the book because it's in Russian and you don't get it in digital form easily. So he said in this book that space travel is feasible, which was totally preposterous at that time. Recoil propulsion is needed to move in vacuum, so he had it figured out. Gunpowder is not energetic enough for propulsion, and remember that since the 12th century, every single rocket that I know of had been built with gunpowder. And he said, but there are liquids sufficiently energetic, so there is a loophole. Even if gunpowder is not good enough, there are other liquids that can do it. And he also named them. For example, liquid oxygen and liquid hydrogen would be an ideal propellant combination. And this is very interesting because liquid hydrogen had been synthesized only a few years before in small quantities. And he was thinking about burning it in tons and tons of stuff, where 1 kilo would cost like 1 million euros, okay? So he was way, way ahead of his time. And as is the case with such pioneers, nobody understood what he had written in this treatise. Well, anyway, 20 years passed, and Mr. Obert published a book. First, he tried to write a dissertation in Göttingen, where he was studying astrophysics, astronomy it was called in that day. And he called it Rocket to Planetary Spaces, die Rakete zu den Planetenräumen. And his professor, Mr. Wax-Wolf, said, well, it seems all quite well, but it has nothing to do with astronomy. So, no, I cannot pass this dissertation. So he went on and published it as a book, and later on got a diploma thesis for this book. And this book was read throughout Germany and spread to other parts of the world. And in the end, this book made that these three Rocketeers knew each other. So, what did he write in this book? It is possible to build a device that can go beyond the atmosphere. It's very similar to what Tsiolkovsky found 20 years earlier. These devices will reach velocities to leave Earth's gravity well. Again, preposterous. And such devices will be able to transport humans. Impossible. So, and this was the really important prophecy, the realization of these devices will be feasible in the next decades. This is quite well, knowing that we landed on the moon like 46 years later. So, another very important point was Goddard's invention of liquid propulsion. The first flight was on 16th of March of 1926. And he used gasoline and liquid oxygen. The tank, indeed, was below the burning chamber, totally atypical to today's design. So the burning chamber is this little black thing up there. And then we have the Laval nozzle here, which was totally new, which wasn't used before. It pays out to be physics professor sometimes. And it has a specific impulse of about 170, which is almost the double of gunpowder. Not very good compared to modern engines. But anyway, he only reached 56 meters, and it lasted 2.5 seconds to reach this height. Well, unfortunately, there was a camera running, but before the rocket could lift off, the film was empty. So, no movie. You know that moment, right? You really get something right, and then, no, sorry, but you didn't press the button. Okay, that happened to Mr. Goddard too, so. Okay, let's talk about foundations. What do we need to make rocketry, to be a rocket scientist? Of course, mathematics. And mathematics is everywhere, I don't have to tell you. Linear equations, algebraic equations, differential equations, calculus, integration, everything else, and some specialized things too. So mathematics is very basic. Then, of course, physics. Although we don't need very sophisticated physics, just a classical one, so classical mechanics, classical gravitational theory, of course. If you get close to planets and moons, maybe you need some extension of the normal point-like theory, but this is not really complicated. Then, and this is for the pyromaniacs here, we need thermodynamics, because this is a theory of combustion. Yeah? So combustion is today very important, especially for high-thrust engines. And this is almost, I mean, everybody knows this. Yeah? We have the burning chamber here, where the combustion takes place, and then this bell-shaped nozzle that expands the gas, and by expanding the gas, transforms the inner energy into kinetic energy of the gas, thereby propelling the rocket in the other direction. Then, of course, aerodynamics, at least as long as you stay within the atmosphere, this is very important because this is the main force on the rocket. Yeah? If you have seen rocket launches, there's always this point of max Q. Max Q means that the rocket is at the point where the most forces is acting on it. It's very dangerous at the point, and after that, it gets down. So, aerodynamics, very important, very complicated too. Orbital mechanics, once you reach space, you will have to understand very, very good where you are and where you're going. So, orbital mechanics and maneuvering. Otherwise, you won't reach the target you intend. This is, for example, the trajectories of Voyager 1 and 2, which was really pure luck to get so many planets in one shot. Yeah, you have to launch it at the right time, otherwise it's not possible. Then you need a lot of mechanical engineering. So this is today much easier than it was like 40 years ago. We have today CAD-CAM, we have CNC milling machines and lathes and everything. So much easier and much easier to reproduce, especially because our materials today are more, if they say it's aluminum, it's aluminum. It's not just some crap. Yeah. So we need a lot of metal working, milling, drilling, whatever. And this is coming now more into focus. You will use composite materials if you need a lightweight structure that is sturdy enough. It's more complicated than cutting metal, but it's really lightweight. It pays off. Then, of course, electronics. Everything that will fly on a rocket will have to be very light and consume not too much energy. Otherwise, the batteries will be too big. This is prohibitive. I mean, we are not in the Apollo era anymore. We don't need hundreds or thousands of watts to run a computer. And this I don't have to tell you, we need a lot of software today. In the beginning, the first rockets were launched without digital computers. They were launched with analog computers. So-called Mischgerät was the first of them. And there was not one single line of code. Remember that. They flew the first rockets with that until the Apollo program. The Apollo program was the first one that really used digital technology. And very important, once the rocket is gone, and normally they are gone very, very fast, the only way to get your data is through telemetry. No other way around. Okay, now let's see how rocketry works. The principle of every rocket is the so-called recoil principle. That states, and this is a direct result from the homogeneity of space, Noether theorem, the total momentum of a closed system appears constant for an inertial observer. Or with Newton, if there are no forces, the total momentum doesn't change. So if you look at a rocket at a certain time, and the next moment, it expels a little bit of mass with a relative velocity u. So this is the velocity minus u in relation of the center of gravity of the rest of the system. Yeah, so you go from here to there. Of course, it's a continuous, but just think about atoms flying away. So anyway, if you say that this is conserved, then the total momentum in this moment has to be equal to the total momentum in this moment, and this leads to the simple equation. I know equations make people run away. This one. And if you look at it very, very closely, you see it's much easier. It's this one. So if you divide it by the time, delta t being, you get a differential equation. Can you integrate, yada, 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 and you get to Tsiolkovsky's formula. He found that in 1800 something, so it's not complicated at all. Yeah? No, really. It's not wrong. It's wrong. Okay. So, well, this thing that I call delta V that stands here, this is the only thing that you really have to remember. Delta V is somehow proportional to this expulsion velocity and some logarithmic of the ratio of beginning and end mass, okay? So, this one here is technologically given by the engine you have. This is a velocity given by gas expulsion, for example. It's in the order of between 1,000 meters per second to a maximum of 5,000 meters per second. If you use electric engines, you can go much higher, but with chemistry, you are bound to this expulsion. And the second term here, the lighter the rocket gets after the burn, the higher the total term gets, but because of the logarithm, the effect is very small. But anyway, you will try it. So what do we need delta V for? You need it to get from one place in our solar system to another, because to get from one orbit to another, you need a certain delta V. Who of you plays Kerbal Space Program? Ah, okay, so, very good, very good, yeah. My little son does too. My wife doesn't like it. Anyway, so to get from the Earth to low Earth orbit, you need an exorbitant amount of up to 10 kilometers per second. That's why it's so complicated to get off the Earth. Once you are on low Earth orbit, it's relatively cheap to get to other. Let's say to a geotransfer orbit is 2.5, so only 1/4. Yeah, and from there to Mars, it's just adding up these ones. It's not that much, okay? It's still something, but not that much as going from the Earth to low Earth orbit. So getting to low Earth orbit is the real challenge. Once you are there, you have all the time in the world. You can use a very, very little engine. This is just very efficient, and you get where you want, okay? But getting into low Earth orbit, this is the lesson you have to learn. That's complicated. Okay, to get there, normally one stage is not enough. So you use 2 or several stages, and then just this delta V just adds up. Yeah, so this is the first stage, and you start with the mass m0, and at the end of the burn you have the mass m1, and then the next stage you start with m1, and the rest is m2, and this has to be as large as possible. So you spend every time a lot of mass, and that's why a Saturn V rocket looks very big at the beginning and very small at the end. Okay, so now let's talk about our projects. Why would we even do that? So for our case, for the FIR, we want to make testing on suborbital flights. We cannot get into orbit now, it's impossible with the resources we have, but we can test it on suborbital flights. It means we just fly to, let's say, 10 kilometers or even only 2 kilometers, and then we can test all the stuff that is needed for a real flight, like telemetry, avionics, everything. Yeah, it doesn't change, it's just a bigger rocket in the end. Then, even if you only go to a few kilometers of height, you have almost minutes of zero or microgravity. So you can do really interesting experiments without going into space. And what we really want to do is cross the Kármán line, because at that moment, the Kármán line is at 100 kilometers, it's just a definition. There's no real line there. You can go up there and look, there's nothing. Anyway. One day we just thought, okay, when are we in space? It is 60 kilometers? No, it's 80, 120, let's take a round number. Let's take 100 kilometers, and that's the Kármán line. Normally you say Kármán line is defined by there is no possibility that a plane can stay up there. You need a rocket. So, and what is very important too is meteorological in situ measurements, and there I want to switch to my colleague, Sean, because he is the meteorologist.
And the mic?
Yeah, Mike.
Thank you, David. Greetings, ladies and gentlemen. So while David has already mentioned that rockets are one of the possible means to access the interplanetary space, and you can do some kind of science in interplanetary space, we can also do some really interesting science without going to the interplanetary space, up to a height of maybe 8 to 10 kilometers, that is the upper limits of the troposphere. In fact, you do not even have to go to 10 kilometers, you just go to 5 kilometers and you can do really interesting stuff. Let us take a look what we can do there. Das, no?
Yep.
Genau. So, here I have quoted a line from a paper from Van der Leij-Martins, and this paper was published in the Atmospheric Chemistry and Physics Journal, which is an open access journal from the European Geological Union. And there he writes that, unfortunately, all the methods that we have today, including today's radio sondes, including today's satellites and radar methods, they are not enough to study, for example, a cloud. Particularly, he emphasizes that the thermodynamics that is happening in the top part of the cloud, which is illuminated by the solar radiation, is entirely different than what is happening in the bottom side or the side parts of the cloud, which is not illuminated. And thereby you have entirely different thermodynamic phases, entirely different dynamics of water vapor condensating and again vaporizing. And this can have really deciding effects on the climate system of this planet. Why this is important for us? Because if any one of you have read the report of IPCC, the last one and the one before that, you will see that the surety that we have on our knowledge about aerosol systems, more specifically on clouds, is really, really low. If you want a quantification, then the amount of error is in the order of 300%. And therefore, investigating aerosol systems, or more specifically, investigating clouds, and the indirect effects, how they influence the albedo of the planet, is really important in order to predict what the planet is going to look like in the next years or in the next decades, and how the climate system is going to be affected by that. Why? Rockets make a very interesting and a very perfect way of investigating that will be cleared from this picture. This is an investigation done by NASA. This is called GREECE, as the country of Greece, but this stands for Ground to Rocket Electrical something Correlation Experiment. And what you can see here is that a rocket is delivering a sonde directly inside an aura. So the Important part here is that a rocket can do really precise sonde delivery, really precise instrument delivery. And this is why this is really interesting. Then we can deliver a device on the top of the cloud or even on the bottom of the cloud. And then we can use these two devices to investigate what has not been investigated yet. In order to do that, we do not need really big rockets. First, let us take a look at this rocket. This is a sounding rocket called Javelin. This was developed to study the upper atmosphere, more specifically the ionosphere, and the ionization properties of the ionosphere so that the Americans could develop radio communication technologies more efficiently. But we will not need that kind of rockets. We'll need much smaller, much low-flying rockets. And Dr. Madlener will tell you more about such kind of rockets and their flight properties.
Thank you. So, as you have seen, Sean is very passionate about clouds. So this is a typical CanSat. This is not our CanSat, this is just one CanSat. It's a very small satellite, really as big as a can, nothing more. And you can today, with modern microelectronics, you can put something in it that can measure whatever you like. Yeah, I mean, there are so many sensors today. Just go on the internet and search for Arduino or whatever, and you get for $50, you get so much that you can, make like 10 CanSats. Anyway, so what do we want to do and how do we do it? Our philosophy at FIR is to keep it simple, stupid, with or without comma. So we use solid rocket engines mainly. We are also working on hybrids, but they're a little bit more complex. So solid rocket engines is what we have used the last 9 years. And they are based on something we call candy. Actually, you can really eat the ingredients. I wouldn't recommend to eat it in block, but it's sugar, it's salt that you normally put in meat so it doesn't get bad, a little bit of charcoal, which is not good for the taste, and iron oxide, which is more healthy. Anyway, we use always common materials, so we use aluminum, we use steel, we use multiplex, wood, we use PVC, whatever. You don't need something exotic like magnesium, aluminum, whatever. Yeah, it's not necessary. Sometimes we use also glass fiber. Carbon fiber is nice, but it's very difficult to handle. It's bad for your lungs, and it's very expensive, so we don't do that. We use standard manufacturing techniques, so milling, drilling, the lathe, turning. These are allowed, and we always use a low budget. So none of our rockets is more expensive, let's say, 2 kilo. Yeah, this is our budget for one rocket. Of course, a lot of money goes into all this running around, going to Denmark or wherever, but the rocket itself, it's very cheap. And to keep the budget even lower, we built them to be reusable. So parachutes. Okay. So what have we done in the last years? This is from 2005. It's called Arguna 1. It was a nice little rocket, 3 meters long, 16 centimeters diameter, so like this. And it could fly to almost 1 kilometer. And this is a flight in, I think, 2006 or 7. This is pure candy, as you can see from the white smoke. This is soda powder, essentially. And you don't see a flame. The flame is very small because this doesn't burn very hot and it has some specific impulse around 140, which is not very good, but it's extremely cheap. Like 1 kilo costs us like €2. And on this rocket, it's just 2 kilos or so. So to build rockets and to fly them, that's not the expensive part. The expensive part is to get there and to get the permission to do it. It's more expensive, today at least. So this is the Arguna 2, which was built a year later and was trimmed to be very fast. It has a diameter of only 11 centimeters here, a slightly larger motor, and it getting up to about 2.5 kilometers with the median motor. The big motor was never used. The big motor, so the aft part is the motor. So the medium motor is like from here to here, that's all. And the big motor, the end motor that we never used, would go up to here. Yeah? And we did never use it because it hadn't the permission to go up to 6-7 kilometers. That's the only problem we had at the time. Anyway, we flew it a few times. This is also, again, normal candy, as you can see from the white smoke. Then we built, in 2008, the Arguna 3, which is not very much larger, but very much thicker. As you can see, this is 20 centimeters diameter, so you can pack a lot of stuff inside it. Yeah, because we understood that with the Arguna 2, which was very fast, it was very difficult to put anything inside. Well, at the time we had no Arduinos. Now it's not a problem anymore. Anyway, in flight it's slightly different because this here is what we call Suka, super candy, which is a mixture, yeah? It's not my invention, it's the invention of Dr. Oeckel, which has a patent on it. He's a member of our club. And the patent is just to protect it so no one can take it away, so everybody can use it. It's essentially candy with a lot of aluminum powder, like 200 micron powder, and it goes really, it has like 170 seconds specific impulse, so it's a lot of more power behind it. Okay, so in 2008, 2009, we thought about, okay, now we build 3 rockets, but we want to go higher, like 10 kilometers or so. And we had contact with the Danish club called the Danish Space Challenge that operate from this little town close to Aarhus. And then we had a motor. We will see it later in action. Here, this section here, this is the motor. This upper section was the recovery section. Here upwards is the avionics bay. We made it shorter after that. This here is the ramp that we built for Poland, but then Poland was so dry that we couldn't go. This was in 2011. They called us like 1 week before. We were ready. We wanted to go to Poland. And they said, no, you can come. Why not? It hasn't rained in like 4 weeks, and your rocket will ignite our wood. So sorry guys, next year maybe. Anyway. So let's talk about part production. I've told you that we use normal manufacturing methods. So this is a lathe. And after a while, it looks like this. Yeah, so this is for the motor, the upper compartment, the adapter. And these are the parts, the couplers, and for the avionics bay, the separation coupler. So these are the normal couplers for the tubes, and this here is for the motor. They were manufactured in 2010. And then we had to make holes in it. I mean, you take a drill, you make holes in it, right? But you have to be very precise. That's not very easy. So what you see here is a stepping motor, which you can give impulses so it turns a certain angle. Otherwise, it will be imprecise. You cannot do it by hand. It's impossible. Again, milling. This takes a lot of time. So to mill a fin like this, it takes like 4 or 5 hours. This is the nozzle combined with the enclosure. So here you see the graphite part. Graphite is really very, very nice to handle. Of course, it's brittle, but it's self-smearing, so you don't have to use any lubricant during the procedures. And this is the nozzle from the other side. So you can see here the throat of the nozzle where the hot gases go through. And don't touch this after test. It's really hot. So let's talk about our launch campaign in 2014. Our colleagues from DSC had the courtesy to bring us over our materials that we left there, the Arguna 4 parts, because we had to come from Cologne and Berlin and Munich and so on and go all the way up to Denmark. So taking the whole rocket every time up and down appeared a little bit futile. So we left the rocket in 2013 there, and they told us, no problem, we will bring it by. And that's what they brought us on Monday. And we were scheduled to launch on Saturday. Okay, so we were like, oops, what do we do now? But the Danish Space Challenge is up for a challenge. So, Danish Soldering Challenge. They really, within a few hours, they could repair it by soldering. This is Dural. This is not very easy. It's very brittle material. They soldered it using nitrogen gas together again. Of course, we were a little bit astonished that Dural could break so easily, so we removed all the paintings and then used fiberglass to reinforce it again. So we were there for 1 week before the launch. We came there on a Sunday. On Monday, we were brought all the stuff from DSC, modulo the fin, and then we started to integrate. So we integrated for a whole week this rocket. This was one step. This is the avionics bay, the upper avionics bay. We can see here on the upper there's antenna. This is just for testing. The real antenna would be more on top. This is an RFM12BP module from HOPE-RF. Half a watt at 70 centimeters, very powerful. Here below, there are sensors, gyroscopes and accelerometers, and here below is a data processing unit, a simple microcontroller, a PHX32A if somebody wants to know. So, this is another view from upwards. So you can see again here the power module, the RF power module. This is just a voltage regulator, and this was the antenna for the tests. So this is during integration. So these are just two simple LiPos. Yeah? It's very simple, just put them on top. And what you can see here is some cables running down to an ADC down at the data processing unit, because we tried to launch this rocket like 3 times, and every time something else happened. The first time, the batteries ran out on us. So we had it on the ramp, everything was ready, and then no telemetry came. We said, what happened? And it was just that the battery died on us. It was the first time in Tranum, in the north part of Denmark. The second time, the Danes switched the place where they wanted to launch to Nymindegab, which is in the southern part of Denmark. And there is very, very fine sand, white fine sand. And indeed, there is a location very close to Nymindegab, which is called Wiedesande, which is white sands, if anybody knows what that is. So, we tried to launch on white sands, but then they got with their truck on this white sand, and it just sank boop, into the sand, and they had to call a crane to get it out again. So no launch at this day. Anyway, so this is after integration, and you can see the look in their eyes. Finally, it's done. Yeah, it was like several hours. This is on the beach. Again, the very fine sand. Here on the left, our meteorologist. Here on the right, the other ones. And on the beach, you really have to work inside a tent, because you cannot work in the wind and in the sand. Everything gets full of sand. I mean, this sand is really strange. You get full of it, like everything is full of it, and then you go off the beach, you make like this, and it's gone. Yeah, it's so fine that it goes into everything, especially into your mechanical parts and lubrication. This is the antenna. This is a circularly polarized antenna, very nice, for 70 centimeters. We had 2 of them. This is one ground station. So we receive telemetry over this antenna. It goes directly to the laptop, and you can see the stream in real time. So these are the 3 parts. Again, the tip here, avionics parts with telemetry, and the recovery part, which is a CO2 cartridge, which is ejected at the highest point, or should have been ejected at the highest point. This is the motor. Yeah, I come to this. This is the motor, with the 18 kilograms of Suka giving about 1.2 tons of thrust for about 3 seconds, which gives the rocket an acceleration at burnout of about 30 G. So it's fast. Yeah? You count to 3, it's gone. I mean, literally gone. And this is the recovery section with the parachutes, and of course, as we are over sea, a buoy, or better said, there were 2 buoys, but only one worked. Anyway, this is the launch. So it's very impressive, and I want to show you on video. Just have to start it up. First of all, first I show you the motor. This was a test performed in 2009, where we were just thinking about the Aguna 4. So there was a test that didn't work out in 2008. So this is a setup, very simple. If you look at it, you can find everything in your normal hardware store, except maybe the graphite nozzle. That's very difficult to get, but anyway. So this is Dr. Oeckel. If you look closely, he's missing 1 finger on his right hand. And yeah, he says he will never again touch chlorates, never. Yeah, he works for this. He lives for this. So he's a chemist by profession, and he worked as director of the Bayern Chemie in Sun, so he knows what he does. Yeah, but even professionals can get sometimes, mutilated, and he's also slightly deaf on one ear. So that's why I always say, please stop doing solid rockets. But nobody can stop this man. So we are in a field, I think it's somewhere in Bavaria. I don't remember exactly. Can we get sound on this?
I think so.
Yeah? Put a little louder.
Moment, I try. Where is this? Oh, there, no?
Here, yeah.
Fünf, 4, 3, 2, 1, 0.
Pop. Wait and see. This Suka is very slow, and we have a reason why it's so slow. We tested it at BAM. It has this BAM certification, which is, in German we say, without BAM, no boom, okay? This is very important. You are not allowed to use such pyrotechnics without proper registration and everything. So Dr. Oeckel has the certificate to manufacture that kind of stuff. And of course, as I said, he had problems with chlorates, so he switched to nitrates, and nitrates are also very volatile. So they tested this motor and they found out that the Suka is extremely sturdy. That is, you can go at it with a hammer. You take it, the piece of Suka, you take a hammer and you can really club it. Don't try this with any combustible rocket fuel. Yeah? But this one is really, really very slow. That's why it takes so long until it gets started. You really need the motor to build up the pressure until it goes. And when it goes, I'll tell you. Okay, so first of all, I will show you the This is a test of the ejection system of the recovery system. So it will put out the parachute. So this is in real time. It will be slightly fast. So I will stop it when it's out. So that was it. Yeah? So this happens in midair in the highest point. It just ejects through CO2. And what we see here, well, this is avionics. And here, connected to a shock band and a carabine, this is a drogue chute from a drone called CL289, which is very cheap, like 10 euro. But it's of the best material. It's aramid. And here, down here, you have the buoy, the one that got destroyed. But one buoy, another one is in the lower section. So there is one shock band that goes down to the lower section, and at a proper time, or height, to be more precise, at 400 meters, a second pyro resolves a junction down there, so the main chute can get out the second buoy. So, and this can be shown also in slow motion, so you can really appreciate what's happening there. Please look for the CO2 snow. I think I have to, this is really slow. Takes a lot of time. I think this is a Casio FX1, I don't know, I don't remember. Just to the end. Now, okay? So this is what happens in slow motion. We made a lot of tests, and this was one very, very spectacular during daytime. We did some tests during nighttime. So this is the launch itself. This is slow motion. I tell you, this is slow motion. This is like half the speed of the real rocket. Bye-bye. In reality, it's like, where did it go? Well, it was very funny this day because we had at the beginning, we had blue skies, really nice weather, and then the clouds came. And then our Danish friends from Danish Space Shuttle, they had also a rocket, a little smaller one, not too small, but not that fast. And it went into the cloud, and in the cloud something happened, like boom. And then on the same trajectory, the rocket fell down. Like, so as if the cloud would have munched it up or something. And then this one got up, and we got nice telemetry. But it went down, and we never found it again. At that day. So we were a little sad, but we had the telemetry. So we were glad and sad at the same moment. Glad because finally we could launch the rocket, and this is sad because we couldn't take it home. But 2 days ago, later, when we were there on Sunday, thinking about nothing, a mail came in and said, look what the cat dragged in. and there our rocket was again. It had survived with one buoy. And it was in Danish newspapers, everything, rocket found at whatever site, and we don't know where it comes from, and who. Yeah. But the chairman of DSC, he's a journalist, no problem. His press release was flawless. Anyway, so that's what we have been doing now. We will try to refit the Arguna 4, which is now in Denmark, using a DART to go even higher. This one reached 6.5 kilometers. I could show you all the telemetry, but it's not really very interesting. It takes a lot of time, but if somebody's interested, please ask. And this will be our next rocket. Okay, there are no lengths, but this is like the same length as the Arguna 4, like 4.5 meters, but like 30 centimeters diameter or so, 20 to 30 centimeters. It's called the Arguna 5, and we have already a mock-up. Not a fly-in version in the sense that it will go like 50 kilometers high, but a mock-up that will go up to about 2 kilometers, just to test everything, aerodynamics, and so on. Okay, so that's for today. Please, if you have questions.
David and Sean, thank you very much for this very, very impressive speech. So now we have question and answers. We have 10 minutes, so please line up behind the microphones. We have 3 over here and 3 over here. While you're lining up, is there any questions from the IRC? Yes?
Yeah, there are. One question was, are there any restrictions or on height or the size of a rocket that you can launch on your backyard or anything? Or are you restricted and it is forbidden?
Are there any restrictions? Well, how can I put this? We are in Germany. Actually, we have been trying to launch rockets from a military ground since 2006, which is now, let me see, well, wait, 8 years. And they granted it us on 8th of December of this year to launch 2 rockets. So we launched rockets in Baumholder. You may have been reading it, otherwise Google it, Baumholder FAR, you will find it. And yes, there are a lot of restrictions. We had 31 restrictions to launch in a military place. So think about launching it in your backyard. Of course, if you go to Denmark, it's a totally different matter. They just ask you, is this a rocket? Yeah. Okay. And don't leave the space. Okay. So it's much easier. But of course, the bigger the rockets get, I mean, the rockets you just show, 1, 2, and 3, they're really model rockets. I mean, they look like big rockets, but they only fly up to 2.5 kilometers. This is still a model rocket. Yeah. Arguna 4 is something totally different. I remember this Danish woman standing there, first having watched their own rocket, and then the second one, the Arguna 4, and she just said, without thinking, wow, that's a real rocket. That made me very happy. Anyway, did this question fully answer? Yeah?
Okay, thank you, David. Gentleman on number 2, please.
Okay, first you asked in the beginning for further reasons to go to space, and I came up with one, actually, because we may need to earlier or rather hopefully later. But my real question is some technical details about the rocket. You mentioned it, right now it's rather a model rocket, and it doesn't really go to space yet. And I'm wondering what the next steps are, especially because I guess you will not get into space with sugar alone.
Well, we don't want to, but there are people, there's a project called Sugar Shot to Space, SS2S. They really try it, but they have a problem because candy, this is sugar, propellant, has one drawback. It's eatable, but it has one drawback. It's brittle. So if you make large grains, let about 12 centimeters diameter the problems start, that when you start up the engine and the pressure peak comes up, then some of the grains may break. And if a grain breaks, that means that the area, the burning area, will vary very fast, which will produce a pressure spike, which will make a faster reaction, which will produce more pressure. You guess it.
Okay, the next question is, you mentioned the price, 2,000 euros, and I wondered what the maximum weight is you can transport up to, well, what Arjuna 4, you mentioned will go 10 kilometers high. What's the payload you can transport there?
Yeah, we are aiming for. The thing is, the rocket is really, really heavy now. We make it that heavy because we cannot go that high. So the last time we had 30,000 feet, which is approximately 9.1 kilometers of ceiling. So we didn't want to make a very agile rocket, very, very high-going rocket. So we were happy that it stayed below 7 kilometers. As you have to have some margin, otherwise they don't believe you that you really, Anyway, we could transport like 5 kilos or so at the moment. Of course, there's not enough space unless you put in steel or something. So something like 2 kilograms is more realistic. Yeah, that's totally enough for a lot of avionics.
Okay, and my last question is about testing. It's quite difficult to test the software which goes high there if it is expected to experience in excess of 40 Gs of acceleration. I guess you do not test this in the lab before.
Well, yes, you can test it. It has more than 40 Gs when it hits the ground. Try it.
Okay, but it's not okay. Probably.
Okay, David, thank you. Gentleman at number 1, please.
Yes. In Kerbal Space Program, I learned you need some kind of control for the rocket so it doesn't veer off. Did I miss that part, or can you explain how you control, wie die Steuerung der Rakete funktioniert?
Yeah, control. Well, we would like to control it. The problem is that as I said, keep it simple, stupid. So at the moment, no control. Of course, the rocket is stable, so it doesn't go anywhere we don't want it to, but it's passively controlled on its trajectory. So you once put the ramp up and you aim for the direction, and that's it. And because they accelerate so fast, they are immediately stable. Yeah, the momentum chord is like half a meter, so there is absolutely no motion. It's like straight arrow. And of course we would like to control it, but what's the point at the moment? At the moment there's no point because we have solid rocket motors that burn out in 3 seconds. So after that, what do you want to control? No motor burning anymore. It's another thing if you have hybrids which accelerate with like only 2 G or even lower, then your rocket is totally unstable and you need control. And there's no way around it. So what we will do is take this very nice O motor, propel it to 30 Gs up to 1.7 Mach, and then put a little dart on top with a little hybrid motor, so it's stable. Yeah, so we can go up to 10 to 20 kilometers without new technology, or almost no new technology. Yeah.
Great. Thank you. Number 2, please.
You maintained that there are laws in Germany. You said without BAM, no boom, or something.
Yeah.
If you build hybrid motors, are there restrictions too, or how does it work in Germany?
Psst. There are no restrictions. Psst.
Yes.
Anything from IRC? Okay. Number 2, please.
I've seen people using balloons to do measurements. That sounds a lot cheaper and easier. It's a lot less spectacular, but why aren't you using them?
That's the point. That's the point. It's less spectacular. Number one. The thing is, of course, balloons are very easy to get like to 30 to 40 kilometers of height. That's true. And if you really want to just go up to this height, use balloons. It's okay. The thing is, don't expect it to come back, number one, or it's really difficult to get it back. Okay, rockets are sometimes also difficult to locate, I know. We have lost some of them, but we always found them in the end, like a few weeks later or so. So balloons are a nice thing, and we wanted to do it, but we just hadn't had the time. It's all. You can use balloons, no problem at all. Yeah, but don't expect to go to 100 kilometers, not possible. Yeah, in the long run. Yeah, but balloons are a nice thing, unless you want to launch rockets from balloons, which I don't recommend.
Okay, number 1, please.
Once you get the sensors up to the height that you want, you're only going to get, if you don't have anything to keep them there, 1 or 2 seconds at most of readings. Can you comment on how you get readings?
You need to have a sensor that is fast enough with a sample rate of, let's say, 10 hertz or so. Then you will have in this 2 or 3 seconds like 20 to 30 data points. What do you need more? I mean, how long do you want to stay up there? Take a balloon if you want to stay up there longer. It's a valid point. The thing is, using a rocket, you get a profile, an almost instantaneous profile of all the measurable observables from the ground to the top, fast. With a balloon, you take several minutes to half an hour to get through all of this. And you get it twice, up and down.
May I also make a comment here?
Yeah, sure.
Well, there's one more thing. The delivery of the device is very, very precise. So if you have a particular cloud layer, for example, you want to investigate, then you will not use a balloon because the crosswinds may drive the balloon somewhere else, somewhere far away from your cloud or somewhere far away from your halloed zone. You'll use a rocket which will directly deliver your device where you want it to be.
Yeah. Okay, thank you. Number 2, please.
Yes, if you use GPS with your rocket, does it actually maintain a lock on the signal?
That's a real problem. With the Arguna 4, I didn't tell you. The thing is that the Arguna 4 was a full metal jacket, so no GPS receiving. And it went up to 6.5 kilometers, and we anticipated to go up to like 7.5-ish, but it didn't, because the drag was higher than anticipated. But that's why you do the flight, right? You don't know everything. Aerodynamics is really complicated, especially with such a strange rocket. It's very, very strange ratio of length to diameter. And so the GPS receiver was inside this full metal jacket, so no signal at all. And our idea was, while it comes down, we'll find a fix, because we had calculated it had 3 minutes to get a fix. Okay, in theory. The problem was that when it opened like 10 seconds too late, because somehow, we don't know why, the two avionics computer did not detect the highest point. This is a software problem. We are not responsible because this stuff was bought, okay? So it was the only equipment that was not made in-house, okay, and it failed. So we have learned that lessons. We will make our own avionics the next time. Anyway, it fell like for 10 seconds, and you can imagine if you let something fall for 10 seconds, it has like 360 kilometers per hour, and then it opened, like you saw there, in midair, and the parachute, the drogue chute, was especially designed for such a case. Otherwise, it would have just ripped into 1,000 pieces. So it just ripped at one point. And the rocket fell faster than expected. So after 120 seconds of full telemetry, and the first fix showing up, because we saw the time, it fell into the water. So we had no data. But in principle, if you put on a fiberglass radome from the beginning, what we'll do next time, then you will get to fix at least during the time he recovers from this very fast ascent, because of course this is beyond the parameters of normal GPS systems. There are people that have a pimped up GPS system, maybe sitting here in the room. Yeah? If somebody thinks about this, come to us. Really interesting device.
Okay, thank you. Some question from IRC?
Yeah, there was another question. What are your problems or points against using the balloons instead of the rockets?
No. I have no points against using balloons instead of rockets. They are just totally different. The one is very pointy, and the one is very round, and the one goes very fast, and the other very slow. Yeah. I have only one problem. Launching rockets from balloons, because pointy and round, no good. Okay?
Okay, 3 more questions. We start over there, number 1.
You spoke about sensors. Maybe I didn't get it, but could you please explain a little bit more about the sensors you're using and what do you do with the data? And maybe you can especially comment on whether you thought about plugging a camera on your rocket.
What was the last part?
A camera.
Yeah, we had a camera. It was lost. It was lost during integration. It's worse. We had the camera there. We had the space there in the avionics bay, and we don't know exactly what happened. Somehow the USB connector got loose and it was destroyed. We tried everything to revive it, but it was dead and we couldn't get a new one because it was...
Do you have a film of that? Do you have a movie of that?
Of the destruction of the camera?
From the camera. So that the camera filmed until its end.
No. Before the launch, during integration, the camera was destroyed by integrating it. So we now know that we need a backup camera, okay? Okay. No, but the question of the sensors is of course interesting. We use inertial measurement sensors, which are totally common nowadays. You can buy them like 10 degree of freedom sensor boards on the internet for like 15 euros, where you have a gyroscope with all three axes, the accelerometer, and the barometer. And we also used a module which goes up to 24G on all three axes additionally. So you can follow the trajectory of the rocket. And this was on board. And of course, the most important thing for the height is the barometric sensor, which was a BMA 180 of Bosch, which has calibration on board and everything, very nice temperature compensation, and extremely cheap. So there are other sensors too, but they are so dead cheap today. It's just no comparison to like 10 years ago, where you really had to make a bridge and a very high, sophisticated 24-bit AD or whatever. Yeah, it's very, very cheap today. So we had just trajectory measurements, so inertial measurements, and the pressure. And we wanted to do also measurements of the temperature on the tip, but that didn't work out because we had a problem with the antenna. We had to change it, so there was a temperature sensor on the tip because you would have the stagnation temperature, and from that you can also deduce the speed of the rocket relative to the atmosphere. Yeah, so these are the typical observables that we used at the beginning. And of course, later on we want to use more meteorological observables.
So you are storing the data of that sensors on site? What?
Luckily we didn't, otherwise we wouldn't have had 1 byte. No, we send it directly as a stream downwards on 70 centimeter band. It's not a lot of bandwidth, that's why we don't have too much data. It's like 30 kilohertz or so on bandwidth. And we send just NMER sentences downwards. So like the GPS sentence, you just get an ADC sentence and an EMU sentence and so on, and just stored on 2 separate locations, on 2 laptops, in real time. And of course, we have also an SD card on board where it is streamed on, but if the SD card is lost, it's lost. No, that's the problem.
So you can reproduce every launch you do with the data?
Yeah.
Sorry, we're running out of time, so one very short last question, and then we have to close it here.
Right. I have a short question regarding propellant. Some years ago, I read about ALICE propellant consisting of ice, water ice, and aluminum powder. Could you tell us something about it?
Yeah, sure. It's water and aluminum. No, it's very fine aluminum, and the principle with sugar, azúcar, and this ALICE is almost the same, because as you know, carbohydrate is just a carbon skeleton with a lot of water around it. So what you do is that the water burns aluminum, while then the carbon also takes a little bit of the water, and then you have CO2, aluminum oxide, corund, and a little bit of sodium, sodium carbonate. And the thing with ALICE is that it's really difficult to store. So unless you go to the Arctic or Antarctic, not so practical, because it has to be frozen. Then it's a nice propellant. I read a lot about it because it has a very high specific impulse, and it's almost inert during handling, so it's very nice, but it has to be cold, really cold. And this was like spring in Denmark. It's warm.
Okay, thank you. David and Sean, thank you very much for this very impressive speech. A round of applause.
Thank you.